Okay. So hello, sorry for the delay. Again, some technical problems. So what we started last time was, after looking at proposition logic, equation, and uninterpreted functions, we look at more complex or more expressive logics. And such logics can encode problems like we looked at the Christmas problem last time. And these problems, the encoding of such problems, are in general Boolean combinations of constraints from some more expressive theory. For example, in this case, it is the theory over the integers with addition, so linear integer arithmetic. And one way to check such formulas for satisfiability, and if we can check them for satisfiability, we can do it also for validity, so we can solve the proposed problem. One way to do this is SAT modulo series solving. We already looked at this picture last time. SAT modulo series embeds a SAT solver. Oh God. Embeds a SAT solver which searches for satisfying solutions for the Boolean skeleton of the problem. That means it does not look into the theory, it checks an abstraction of the formula. And in order to be complete, it communicates with the so-called theory solver, which extends the search of SAT by checking theory constraints. And the communication is in two directions. First, the SAT solver sends some requests to the theory solver, and the theory solver gives some feedback about the result of his check. So let us look at an example to look how it works. This is our Christmas problem. You see it's a Boolean combination of constraints. That means you have conjunction and disjunction. Basically, we can also have negation, but in this logic, negation can be eliminated because it just turns around the order sign, the comparison sign. So what happens first, I go back one slide. This is the formula that is the input to the SMT solver. And then we make now build this Boolean abstraction. And this is similar as the Boolean abstraction that we made, for example, for equations, in that we replaced each equation by a Boolean variable, and then we added new propositional clauses to state transitivity of the equation. In this case, we replaced by Boolean propositions the theory constraints. In this example, linear arithmetic over the integers. So for example, P1 equals 0 will be just replaced by a Boolean variable A1. And you see, this is the Boolean skeleton. Each constraint is replaced by a Boolean variable. So now I have a proposition logic formula. What is the relation between these two formulas regarding satisfiability? Can I tell for some direction? For example, if this formula holds, then if I have a solution for this, then I also have a solution for this, or the back direction.
That's one. So if we have P, that the upper half is satisfiable, we have a satisfiable solution, a solution for the lower one.
Exactly. So the lower one is an abstraction. This is weaker. It has more solutions. And if I find a solution for this one, how can I check if there is a corresponding solution also for this one, for the more concrete one? What do I have to do? So assume I have here solution, true are A1, A4 must be true, let's say A5, and these three. If these three are true, then I have a solution, actually independently of the values of A2, 3, and 6. But of course, this does not have to be true in the theory, because P1 equals 0, and this constraint corresponding to A4 and for A5 and 7, 8, 9 together does not have to be satisfiable. If they are together satisfiable, then I also have the solution for this problem. Yeah? If they are not satisfiable, then this given solution for the Boolean formula cannot be extended to the theory. And what can I do then? Yeah?
Another formula that states that this combination of assignments is not valid, and go on with that problem.
Exactly. So what I do is that I have a Boolean formula. If I find a solution, then I make a theory check, and if it is unsatisfiable, kind of this communication, then I add a new clause which refines the abstraction. That means which kind of encodes what was the reason why this combination of the theory constraints was not satisfiable. So let us look how it works. There's this Boolean abstraction, and we start with the SAT solver. So we check it. Just to refresh how SAT serving works, we have variables A1 to A9, and now we need some heuristics. So let us say that we take just the syntactical ordering, and we always assign false to the decision variables. So what happens? First, at decision level 0, those literals will be assigned, which must be true because it is a one literal clause. So it is 4, 7, 8, 9. They are here. Then I propagate. They do not propagate anything because in the other clauses they do not appear. Now at decision level 1, I can assign A0, the first one in the variable order, to false. So this literal becomes false, but it does not imply still anything. Now the next assign at decision level 2 is A2, is false. And now in this clause, since A1 and A2 are false, it will imply that A3 must be true in order to satisfy this clause. Now I can continue. The next unassigned literal in the order is A5, and if I assign false to it, then the third clause will imply that A6 must be true. So I found a satisfying solution for my Boolean skeleton. And then I ask the theory solver if the solution I found also consistent in the theory domain. So I take those theory constraints which are true in my assignment. This is 4, 7, 8, 9, 3, and 6. And I send them, these are the red ones, I send them to the theory solver, these are the encodings. So the theory solver gets a conjunction, a set of theory constraints. Now question. Here I state that I send the true theory constraints, which assign the value true in the Boolean abstraction. Now if the theory solver tells me they are satisfiable, I state that then I know that my formula is satisfiable. Though I do not know if they are consistent with those constraints which are false. That means whose negation should hold. What is the reason for this?
It might turn out that in the solution P2 is 1, for example, and then A2 would be true, false. No, it could turn out that in the solution P2 is 0, then A2 would be true, but we assume it would be false. So it might give an inconsistency.
Yeah, but do I know that there exists a modification of my solution? That means, do I know that it is satisfiable? Perhaps not with the current assignment. What is the condition of that the value of A2 doesn't matter, let's say?
If it doesn't appear negated, then I can always change it from false to true.
Exactly. Yeah, A2 appears in my formula only positively. This is because I encoded a constraint, and the constraints are not negated in my logic. If they are negated, then I just pull in the negation to the equation by turning around the ordering. So for example, if I have not x larger than 0, that it is equivalent to x less or equal 0. So the negation in front of theory constraints I can remove. That means that these auxiliary Boolean variables, the abstraction variables, appear only positively in my formula. So if they are assigned true, then they might be necessary to satisfy the clauses. So I must check them if they are consistent together. But if they are false, if A1 is false, then in this clause, this literal does not contribute to the satisfaction of the formula. Especially if I make it true, it would be also a Boolean solution. So, and I know that A1 or not A1, one of these is always consistent with the rest. Because these are linear constraints, they just define a half space. So if there is a solution, and I have two half spaces, the solution will lie in one of them. So that's why I need only to take the true literals, and I can ignore the false ones. Note that it would not be wrong to take also the false ones. Then perhaps the solution of the formula would take longer because I need to do more checks, but I would get the same result. Okay, so now I need know that I need to check these sets of constraints for satisfiability, and now we start for restricting to the real domain. You do not need to understand that in the moment. We will look at later because this is the simplex algorithm, how we solve it by simplex. The only thing what we look at now is that we had two constraints which were feeded in. First, P3 equals 0 and P3 is larger or equal to 10. Obviously, they are not satisfiable together. So it is good if the solver, the stereo solver, can give back a subset of the constraints which are together not satisfiable. What it helps the subsolver if it would not get a reason for the conflict. It just would get back the answer unsatisfiable. Then I go back one slide. I should put in as this new learned clause to refine my abstraction. I should state that those constraints which are currently true cannot be satisfied together. But here would be now 1, 2, 3, 4, 5, 6 constraints, and the set subsolver, so this one, the P3 equals 0 and P3 larger or equal to 10 together are not satisfiable, it could try it again. For example, by making A6 false and A5 true. So, though it could learn something about the theory, but not so precise, not so valuable as if the theory server can give back a smaller subset, giving the real reason. Not just unsatisfiable, but something smaller which is already unsatisfiable. So we will see that we can get from simplex such subsets, and for this case, for this assignment, simplex could give back these two constraints which are together not satisfiable. Here, this is called explanation. And the subsolver, what does it do with it? Just adds the Boolean abstraction of this theory lemma, which is a tautology, to the closed set. So now we have a refinement. Our current assignment doesn't fit with this refinement anymore because 3 and 7 are together not satisfiable. So now I have actually an asserting clause, so I do not need to make conflict resolution. What will be the next step that the subsolver could do now? In the sub procedure, we also got conflicts by Boolean propagation, constraint propagation. But those conflicts were due to clauses which were there from the beginning on. So if I, for example, state A or B and A or not B, and I assign a decision level 1, I assign not A, then it will lead to a conflict. And then I would, let's say this is the conflicting clause A or not B, then I take the implying clause for the last literal in this conflict, so I would make resolution with A or B, and I would get the result that A should hold. Now this is the conflict resolution mechanism for the subsolving. Now it is different, because now we got, after we have searched for a complete solution, we got a new clause. And this clause can state a conflict at an earlier decision level, not at the last one. So what would be nature to do now in this case?
You have to go back to the submission decision level.
Exactly. So in this case, I would go back first to decision level 2. So I would undo 3 to the last decision level in my conflicting clause, and I would do conflict resolution. And in normal SAT-solving, in the SAT-solving procedure, the conflicting clause, where the conflict appeared, has always at most 2 liters at that level. That means I always have to apply resolution to get an asserting clause. Now, it is not always the case. Like now, the clause that I got is already an asserting clause at decision level 2. So what I do is I just backtrack, and at this level I will use my new clause for implication, so for not A3. Sorry, these should not be here. They are undone. Not A3, and with the new clause I could imply, from A3 I imply, from A7 I implied that A3 must be false. And now I do not have any further propagations. A3 makes this clause true, but there are no new more implications. So I made my current assignment, partial assignment, consistent with my formula, and I can continue and search further for a new solution. We were here. So the next unassigned literal in the order is A1. I assign false to it. This will imply by the first clause that A2 must hold. Then I make a new decision. The next unassigned literal is A5. It implies by the clause containing A5 that A6 must be true, and I have a next complete assignment. And I do the same. I collect the theory constraints which correspond to true abstraction variables, collect the theory constraints corresponding them, and give it to the theory solver. It checks again. So this is for the check we will look at later. Important now that it is again not satisfiable, and we get again a subset of the constraints, namely in this case P2 equals 0 and P2 larger equals 5 are not satisfiable together. So we again go back with this explanation and refine the abstraction by adding a new clause. Now you see where are these variables, 6 and 2. Is this again an asserting clause? So I do not need to make resolution. I will just undo decision level 3, and my new clause will give a new implication at decision level 1, namely that not A6 must hold. So A6 is false. A6. So, and I continue with the SAT solver for searching for a new solution. Here I have A6 false, and if I propagate it, this new assignment, then I will get by this clause that A5 must be true, and I'm done. All variables are assigned. So I go again to the theory solver by collecting the true theory constraints which result in this set and sending it to the theory solver. The theory solver now, in this case, finds a solution. What happens now? What does it mean for my original problem? So the SAT solver found a satisfying solution for the Boolean skeleton, and the theory solver find a satisfying solution for the true theory constraints. What does it mean?
Yeah, all variables have a solution. I still have to check the Boolean variables that were set to false if I have to change them.
So if I want to have a satisfying solution for the concrete problem, then I have to do this. Yeah, then I have to check which of the negated or the non-negated other constraints are consistent with this solution. Actually, I have to plug in this solution, then I already eliminated. Yeah, exactly. I can plug in this solution to the other ones, and then I will probably already find out which way they are satisfiable. If not, then I have to continue the check. But if I do not need any solution, then already with this answer I know that the problem is satisfiable. So that's why in this case already the theory solver can state satisfiability, because if it does not need any solution but just the answer to the satisfiability problem. If also this combination would not be satisfiable, and the SAT solver already found all satisfying solutions, and all of them were unsatisfiable in the theory domain, then I know that my problem is unsatisfiable. Now, I tried all combinations of constraints which would satisfy the Boolean skeleton. If none of them is theory consistent, then the problem is unsatisfiable, either due to the Boolean combinations or due to the theory. So, now the change to the last slide is this less lazy. Before I go back, we had full lazy SMT solving, and now we have less lazy SMT solving. What is the difference? In full lazy SMT solving, we always found a full Boolean solution for the Boolean skeleton. However, this may lead to long search. If you have a lot of clauses, a lot of variables, then finding a Boolean solution can already be complicated. And perhaps already at the very beginning, you made some assignments which are not consistent in the theory. So it would be better to already contact the theory solver for a satisfiability check for a partial solution. Usually in SMT solvers, this is done after each decision level. However, this poses some requirements on the theory solver. If I add here, make a decision, make some propagation, and then collect the constraints, send it to the theory solver, and it tells me satisfiable. This is the usual answer. So conflicts happen much more rare than satisfiability. Then the SAT solver will take the next decision level, make further assignments, and then collect the new constraints and will give it to the theory solver. And now the theory solver starts the check again. So it first checked the set C1, and then now it has the set C1 union C2 of constraints. Yeah, C1 corresponds to the first decision level, and C2 is the set of constraints from the second decision level. Then the theory solver makes a kind of double work, because it already knows that C1 was satisfiable, and it would be good if it could reuse the check for C1 to check the union of C1 and C2. And this is what we call incrementality. So it would be for efficiency advantages if the theory solver could work incremental. It gets a set of constraints, checks it, then it gets additional constraints in case it was satisfiable, and it reuses the previous state of the check to extend it to the new constraints. Also, this corresponds to further property, namely, if the SAT solver finds a conflict, it will backtrack. And of course, the theory solver must also be able to backtrack. So if the second decision level is undone, then it should be able to remove also those constraints from its current state and continue the next check from the check state of C1. So incrementality and backtracking should be supported by the theory solver. And the last requirement, which you already have seen, is generating explanations. So it does not only should give the answer yes or no, satisfiable or not, but if the set of constraints is not satisfiable, it should be also able to give a subset of the constraints which are already unsatisfiable. These subsets are called infeasible subsets, And what we aim for are minimal infeasible subsets, minimal in the sense that if I take away one constraint, it becomes satisfiable. That means in this set, each constraint is necessary for unsatisfiability. An example, we had, I cannot exactly remember, but something like P1 equals 0 and P1 larger or equal 5. This would be a minimal infeasible subset, because if I take away one of the constraints, the rest becomes satisfiable. However, if I have something like P1 is larger or equal 1, then it is not minimal, because if I remove either this or this constraint, the rest remains still unsatisfiable. This is not global minima, but local in the sense that perhaps there is another set of constraints which is even smaller, but this one is a local minimum because I cannot take away any of them without getting a satisfiable subset. So these three requirements, incrementality, generating infeasible subsets, where minimal infeasible subsets are the best, or backtracking. We will only discuss minimal infeasible subsets for explanations, but there are also theory solvers which give an explanation which is not a subset of the constraints it got, but it contains new constraints. It can be some bounds or something like new constraints which are implied from the original set of constraints which it got. But we will not deal with that kind of explanations. We will restrict in this lecture to infeasible subsets. So, if I find the other slides, then today we will look at one very simple technique for checking satisfiability of linear real arithmetic constraints. And we will also see that this is not very efficient, but it is easy to understand, and probably you all already used it, even if you do not know it under the name Fourier motzkin variable elimination procedure. So what we start is, we already know this example, and we had here a Boolean combination of theory constraints, and though these are integer, we look first at real arithmetic. So assume now that these variables have real valued variables. So what we consider in the logic is the conjunctions of linear constraints over the reals. What does linear mean? What is not included? Multiplication is not included, so I have only addition. Multiplication, here I have a multiplication. So if I don't have multiplication, why do allow such terms? And let's ask what are Aij. Are rationals, or we could also take, let's say rationals. And Xj are variables from the reals, and Bi are also rationals. So Aij and B are constants, and Xj are real valued variables. So such terms or such linear constraints are evaluated in the context of an assignment, where assigns each variable from B a real value. So especially Xj is evaluated by mu. So then let us come back to the question, if I do not allow multiplication, why is it allowed to multiply a constant with a variable? If the constants would be from the natural numbers, what is 2x? Can I define it also without multiplication? X plus x. So I can extend it also to the rational numbers by just multiplying with the largest denominator. So I can always express this kind of multiplication by addition. So assume we have a set of such linear constraints, the sum of constant time variable and a bound in one direction. And we would like to have the satisfiability question solved. So we formulate our problem as a matrix in that we have here the constants, the weights for the variables. Here we have the variables and these are the bounds. So I can write my problem in a form AX less or equal B. The earliest method for solving such linear equalities goes back already to 1826. Was discovered by Fourier and also later handled or discovered by Motzkin or reformulated. That's why it is called the Fourier-Motzkin variable elimination. The name variable elimination already suggests that we eliminate variables, and the goal is, if we have a formula phi containing x and some other variables y, then we would like to transform it to another formula phi, let's say hat, which contains only the variables y without x, and they are equivalent. Equivalent means that, let's say, they have the set of solutions. So if for a certain x and y, phi is satisfied, then for the same y also phi hat is satisfied, and the other way around. If phi of y is satisfied by a certain vector y, then there exists an x such that the left-hand formula is satisfied with the same assignment. Actually, what we would like to get now is only satisfiability equivalent, but this transformation is completely equivalent. The basic idea is we pick a variable which we would like to eliminate, and we put requirements on the lower and upper bounds on these variables. The idea is very simple. If I have a variable x, and I can transform my formula such that I get some lower bounds, I put now non-strict inequality. We can also have strict ones. I have n lower bounds and m upper bounds, and the domain is the real. Then how can I eliminate x? How can I state some properties which assure that if the property holds, then there exists an x satisfying these bounds? Assume we have L1, LU. I just take the first pair of lower and upper bounds. Then I have L1 less or equal x less or equal U1. For these pairs of bounds, which is the condition that there exists such an x?
Lower, not lower equal. So we can just say L1 lower than U1.
Yeah, even if they are less or equal in this case,
yeah,
it fits. Then I just take the same value. If one of them is inequality, then this must be held for a strict inequality. Yeah, this is because in the reals between two values, such that one is less than the other, there exists always another real value. So this is the basic idea for the elimination. And let us look a bit formal. The first condition is that I can put lower and upper bounds on a variable. That means it appears always on one hand side of an equation or an equation. And this is possible because we have linear constraints. For nonlinear constraints, this is not doable anymore from a certain graph. Okay, so what we do is, if we pick variable xn, then we partition the constraints according to if this constraint puts an upper bound on our variable or a lower bound. For example, here, the first step is xn is now the last element in this sum, so I bring it to one side just by making minus this sum for all j in equal n, so for j1 to n minus 1. This is an if and only if. And then I must check this coefficient. This coefficient can be positive or negative. So if this coefficient is positive, then I can divide by the coefficient, getting an upper bound on my variable xn. If it is negative, then I get a lower bound on xn. What happens is if this coefficient is 0? What kind of bound is it? So I have here this constraint, and this coefficient is 0. What kind of bound is it on xn? None. So in this case, it does not put any bound. Actually, xn does not appear. It appears syntactically, but doesn't appear semantically in this equation. So I collect all upper and lower bounds. Let us look at here. What kind of bound puts the first constraint on x1? Is it a lower or an upper bound? It's an upper bound. The second one also, because here I just add x3, so I get x1 less or equal x3, so it is also an upper bound. The next one is a lower bound because the coefficient here is minus 1, so negative. And the last one does not put any bound because x1 does not appear in it at all. Okay. Now, we have bounded variables which have lower and upper bounds. We might have also the case that one of these sets is empty. For example, in this case, what kind of bounds are put on x?
Upper one and lower one. Two upper ones.
Two lower ones. Yeah, x is larger than something, so I have a lower bound on two lower bounds on x and no upper bounds. So what does it mean? How can I eliminate now x? The case gets simpler. If x, there is no upper bound on x, but a lower bound. If I have a solution for the other variables, what is the condition to have also a solution for x?
I can eliminate the weaker bound, so the lower bound is the lower one. The lower bound.
Okay, I do not know because there are also variables in the bound.
If we have an assignment for the other variables, we know.
Okay, that's true. But perhaps I know also some more.
Yeah, and if we have a solution for the rest, then we can choose this as the maximum of over all other bounds. And if we know we are in the rational number, there always exists a maximum which is at least great enough.
Exactly. So for each number, there exists a larger number in the reals. That means if there are only lower bounds on x, never mind how the values of the other variables look like, I will always find the value for x that is large enough to satisfy all lower bounds. So what does it mean for eliminating x from this constraint system? How does the equivalent constraint system without x look like? Yeah. Remove them because they are always satisfiable. you can always find, never mind what is the value of y, you can always find a value which is larger than 3 and larger also than 7 times y. So forget about it. So what is about the rest? Can I eliminate another variable this way?
Yeah, I can eliminate y, because there's only one lower bound for y.
Exactly. So the same holds for y. I can eliminate it. What is about the rest?
Yeah, since there is only one variable left, we now can check whether the equation holds. And well, of course, there is a solution from that, and so there is a solution for the whole equation.
Exactly. So now I must apply this combination of bounds, and how that works is if I have a lower bound and an upper bound, and my variable that I would like to eliminate is in between, then I just add the constraint that the lower bound must be less or equal to the upper bound. Similarly, if I have the inequations, let's say beta L is less than xn, is less or less or equal beta u. What is the constraint? What is the condition for the existence of such an xn? Yeah, this corresponds to the interval with the beta L and beta u. Never mind what is the value of beta L and beta u. Such an xn exists if this interval is not empty. Yeah, note that this is an open, left open interval. So that means I must add beta L is less than beta u. This assures that this interval is non-empty, and then these inequations can be satisfied. So there exists an xn for each value of these betas. So again, our example, we had already that x1 and x1 in this equation define a lower bound on x1, this one an upper bound, and this none. So if we want to eliminate x1, what do we do? Which constraints do I have to add?
Combination of 1 and 3, combination of 2 and 3, and yeah, you also use 4.
And 4, exactly. So what is the combination of 1 and 3? Note that 1 is this constraint. If I bring x1 to one side, and this one is x2 plus 2x3 is less or equal to x1. So what is the combination of 1 and 3? The lower bound is x2 plus 2x3 less or equal to x1. The upper bound is x1 less or equal to x2. So what is the condition for this interval not being empty? Two x3 less or equal to 0. And from 2 and 3, which condition assures that 2 and 3 define a non-empty interval for the values of x1? Exactly. And I take the last one, which was not a bound, and these 3 constraints are equivalent to these 4 constraints. let's say, satisfiability equivalent. They're equivalent in the sense that 1 to 4, the solutions in 1 to 4 is if and only if there exists in X such that the solution of 4 to 6. So I have now 3 constraints, and the next variable, I have x2 and x3. I have the choice. The better choice would be actually to eliminate x2. Why? Yeah, not only less, but the main point is, what would be the condition for eliminating x2? Yeah, we do not need to add any conditions because it doesn't have a lower bound. That means for the reals, for each number, there is another number which is smaller. So never mind what the value of x3 is. I will always find the value for x2, which is less or equal minus x3. So that's why I could just remove equation 6. Oh, sorry, here I have also one. This I didn't see. No, I have a lower and upper bound. Okay, then, sorry. I thought we have only these two equations. Then I have also an x3. No. This is the only equation containing x2, so it does not have any lower bound, and independent of the value of x3, I will always find the value which satisfies this inequation. So I could just remove this, and I would keep 4 and 5. But instead now we eliminate x3. What do I do to eliminate x3? Now the algorithm collect the lower and the upper bound and add for each pair of lower and upper bound the constraint that the interval they define is not empty. So what kind of bounds are these? 4 is a lower bound on x3. Actually 4 defines 1 less or equal x3. 5 defines x3 less or equal 0. And 6 defines x3 is less or equal x2. So I have 2 upper bounds and 1 lower bound. I must combine all lower bound with all upper bound to assure that all the intervals they define is not empty. So in general, again, this picture, if I have n lower bounds and m upper bounds, then I must add for all lower bound and for all upper bound that the lower bound is less or equal, the i's lower bound is less or equal than the j's upper bound. In this case, this is a combination of 4 with 5 and 4 with 6. So from 4 with 5, I go back one slide because there we have the lower bounds, that x3 must be larger or equal 1. And from 5, I get that less or equal 0. So I get the constraint that 1 is less or equal 0, which is a contradiction in the reals. So I know that the system is unsatisfiable. Okay, if I would not get a contradiction here, if I eliminate all variables and the end, I have one variable. If I also eliminate the last variable, what do I get? If I eliminated all variables, what is the resulting formula? Yeah, true or false, as we see. So if I get, I just get the conjunction of such constraints. Yeah, and if there is one constraint which is false, then my formula is false because then there exists one interval which cannot be satisfied. And if I get only true equations, then it is true. So after eliminating all the variables, I get the answer to the satisfiability problem. So, the drawback. What is the worst case complexity? If I have m constraints and I eliminate one variable, let's say roundabout, I can get a worst case m squared. Each constraint perhaps define a bound. Of course, it is not m squared, it is a kind of upper bound, but it is in this complexity class. What happens if I eliminate the next variable? And if I have n variables, then the complexity is m to the 2 to the n. So this is a very hard complexity, and that's why this method is not used in general. But it is used sometimes in cases it is well applicable. So for example, if we have some formula or conjunctions of constraints, of linear arithmetic constraints over the reals, then we can use it for pre-processing. If I see that one variable has only lower or only upper bounds, I know that I can eliminate it, and it does not hurt me in complexity. It just reduces the number of constraints. Or if it has just a few, let's say one lower bound and a set of upper bounds, then it is also well applicable because the number of constraints I remove is still larger than the number of constraints I add. Namely, I add only one less than. So if I have, for example, n lower bounds and one upper bound, then these are n plus 1 constraints. Oops. And how many do I add? Each lower bound with each upper bound. That means I add only n constraints. So in these cases, it is well applicable. But in the general case, it is very hard. So, and the bottleneck is a kind of case splitting between the lower and upper bounds. And we will see by simplex how it can be done more efficiently, at least in practice. So simplex is also a method to check linear real arithmetic constraints in exponential time in worst case. But in practice, it works much better, and the logic is decidable in polynomial time. There are also algorithms which solve in polynomial worst case complexity. Why is simplex used is that in practice, simplex works much more efficient than those polynomial algorithms. So this is one case where the theoretical complexity does not always cover practical applicability. Okay, let us do one example to see how it works. We take a set of constraints. Perhaps we could take a subset of our original problem. No, it just takes some new one because these are too many constraints. So assume but I forgot is equality. What do I do if I have something like this, a constraint which is an equality containing some variables?
I replace it by number in the lower bound.
Okay, I could do this. No problem. That would actually give me at the end a point interval. What can I do else, which is more efficient?
You could substitute one variable with the other one.
Exactly.
Eliminate it directly.
The eliminated directly just form this equation such that one variable is on one hand side. So for example here, x3 equals minus 2x1 plus 6. and just substitute x3 by this expression. This way you implicitly push this statement that the lower and upper bounds are not empty to the elimination of the other variables appearing in your lower and upper bounds on x1 in the other constraints. Yeah? Since this equation must hold, you can replace x3 by minus 2x1 plus 6 in all other constraints, and then you are done. You have an equivalent formula which does not contain x3 anymore. This is usually done in pre-processing. Okay, we take some more. For example, we can state that 2x2 plus 5 is larger than equal 10. Okay, we have only 4 constraints. How to check? With the Fourier motzkin variable elimination. What is the first thing I have to decide? I want to eliminate a variable. Which variable to eliminate? Now, which variable would I eliminate? In this case, it would be the most cheap, the cheapest one. Yeah, we just discussed this with x3. So I would reformulate 3 to this equation, and I would just replace x3 by the right-hand side. Actually, x3 does not appear anywhere. That means that if I have the values of the others, I can just compute the value of x3 using equation 3. So I have 3 equations left, 1, 2, and 4. These contain 2 variables, x1 and x2. Which one shall we eliminate first? Is there a difference? Is one of them better than the other one? No. Both have one upper bound and one lower bound, so it doesn't matter in the first instance. So let's say we do it for x1. What does constraint 1 imply for x1? X1 is less or equal minus x2 plus 10. So it is an upper bound. Constraint 2 is directly a lower bound, as constraint 3 does not contain x1, so it is just none. What is the condition for the existence of such an x1? Yeah, that the interval defined by this lower and upper bound is not empty, and the interval is 0 and minus x2 plus 10. So 0 is less or equal minus x2 plus 10. That means x2 is less or equal 10. That means I have a new constraint, x2 less or equal 10, and the old one 4, which did not contain x1, this is 2x2 plus 5 is larger or equal 10. And I have eliminated x1. That means the constraints 1, 2, and 4 are satisfiability equivalent to 1 prime and 4. I have one more variable, x2. I eliminate it also. For that, I again check. Here I have directly the bounds. From equation 4, I get x2 is larger or equal 5/2. Yeah. So I have again a lower and an upper bound, and what I get after eliminating x2, adding the combination of each lower and upper bound, I get that 5/2 is less or equal 10, which is true. That means I find that it's satisfiable. Now, okay, I know that it is satisfiable, but can I also get a satisfying solution? Do you have any idea how I could get a satisfying solution from this proof?
Backward the variable in the way counted and apply a value from the interval stuff there. For example, 2 greater equal 5/2 and less equal 10, so maybe we choose 5 possible value. And then we go back to the next equation for 1. 1 less or equal, then we choose, so it means it's 1 less or equal 5. So we could choose 5 for x1. And last step we solve the equation for x3. So
wait, x, okay. Yeah, I just can compute it.
this always works.
Exactly. So this always works, but at the end we have only numbers. Yeah, lower and upper bounds between which the last eliminated variable should be. Then I can just pick one value, which is in all of these intervals. Any of them I can pick, and this will be satisfiable. So there will exist another value for the other variables in combination with this. Then if I have now, in this case, x2, I can put it in my previous equations, which also contain x1. So I, again, have an equation system which contains only one variable. So I have lower and upper bounds on this variable. I can just pick one value. Never mind which one. For each of these values, there will be a satisfying solution for the other variables. So this way, as you say, we eliminate and then we reverse back and then get a satisfying solution. And if at the end we had non-conflicting intervals, then there always exists a solution, and this existence is independently of the value picked from the interval. Okay. Perhaps we make just a small other example where we have to compare different pairs of upper and lower bounds. So, okay. I have only two variables, x1 and x2. We should decide, again, which variable to eliminate first. Which would be the best? Oh, sorry, this should be x2. So let us just count the bounds. This could be, it is not sure that if by the elimination you get less constraints, that in the whole procedure you get less constraints. But this could be a heuristic. So let us look at x1 has lower bound, upper bound, lower bound, upper bound. So I would get 4 constraints for the non-emptiness of the intervals. And by x2, I have a lower bound, an upper bound, a lower bound, and an upper bound. I get also 4. So actually it doesn't matter. But let us take x1 first. What does it mean? Equation 1 is directly a lower bound. Equation 2 also. gives also directly the bound. This is an upper one and a strict one this case. 3 gives a lower bound. 4 gives an upper bound. And 5 does not contain x1. So this is the lower bound 1. This is the lower bound 2. This is the upper bound 1, the upper bound 2. And I need all combinations. So lower bound 1, bit 1. Strictly less than the upper bound. So here I have a strictly less than sign. That means the lower bound must be strictly less than the upper bound in order to satisfy non-emptiness of the defined interval. And this combination gives me 0 less or equal the strictly less than the upper bound 2x2 plus 3. The second combination, let's say lower bound 1 with upper bound 2, both are non-strict. This gives me 0 less than equal x2 plus 5. Then I have the second lower bound with the first upper bound. Non-strict means x2 minus 1 is less than 2x2 plus 3. And the last combination is the second lower bound with the second upper bound. This is non-strict and states that x2 minus 1 is less or equal x2 plus 5. Okay, I can reformulate it. The first one states that x2 is larger than minus 3/2. The second one states that minus 5 less or equal x2. The third one states that x2 is larger than minus 4. And the last one states that minus 1 less or equal 5. And I have still my last constraint from above, less or equal 2. So these 4 constraints are satisfiability equivalent to the first one, but do not contain x1 anymore. Okay, I would like to eliminate now also x2. We check. I have here a lower bound, another lower bound, another lower bound. I have a tautology, and here I have one upper bound. So the conditions that I get for the existence of x2 is combination of lower bound 1 with the upper bound, lower bound 2 with the upper bound, and lower bound 3 with the upper bound. Lower bound 1 with the upper bound tells me that minus 3/2 is strictly less than 2. The second one, lower bound 2 with the upper bound, tells me that minus 5 is less or equal 5. And the third one, that minus 4 is less or equal 5. So since all of these constraints are satisfied, I again know that it is satisfiable. If one of these constraints would be unsatisfiable, then it would mean that one of the intervals is empty and not satisfiable. Okay. Do you have any questions to SMT or the Fourier motzkin variable elimination? Okay. If it is not the case, then I would stop here now, and next time we will continue with simplex.